All right, well, hello everyone. Welcome and thanks for joining us. My name is Doug Smith. I'm with Doulos, a training company. I'm actually located here in the Austin region. For those of you who are familiar with this area, I live out near Bastrop, have a small farm. So if you're interested in talking about farming, catch me afterwards, and that's one of my favorite topics. But for now, we're going to talk about practical hacks for SystemVerilog coverage. And I have to click on the screen, so give me 1 second here. Okay. So let's take a look at what coverage is offered in SystemVerilog. So of course we have cover properties. Now you may not think of a cover property as functional coverage, but technically you're describing a functional scenario and it's going to say whether it got matched or not. So the advantage here is that we get to use that temporal syntax that makes it very easy to describe a complicated sequence in just a few characters of code, right? You can access those properties through the assertion API, which may not even be aware that SystemVerilog provides a couple additional APIs. But really, there's not a whole lot you can access with these. It just kind of tells you what state your cover property is in. Now, cover properties, since they spawn a thread of execution, they have to be placed into something structural, like a module, interface, or a program block, which is why we typically don't use them in our UVM test bench. I mean, technically, you could use them in UVM if you actually defined your classes within a module, but we never do that, right? We always put our classes in a package so it's all within the same scope, and packages can't have threads of execution. Therefore, we don't use cover properties typically, right? We might use them in our interface or something like that. And of course, you guys are familiar with cover groups. This is what we usually think of when we talk about coverage in SystemVerilog. So we can define our different cover points, and then we can cross those to see interesting functional scenarios. And of course, we can put these cover groups inside of our UVM test bench. We can put them anywhere, right? And technically, there is one other type of coverage defined by SystemVerilog, and that is code coverage. There is a code coverage API if you go check that out in the standard. However, I have yet to see a simulator that's implemented it. So it's kind of, I can't really talk about it. Okay. So just to go over really quickly these types of coverages, here's an example of a cover property. And not to belabor this, but here it's just saying when I see a rise on rec, 1 cycle later, I should see rec and ACK between 0 and, you guys know what dollar is? End of simulation, right? Infinite time. So I should see rec and ACK followed by not rec. So that one matches. And then, of course, on the end, we have one where it's not going to match. But the point of this slide is that when you have a cover property, you can drag it into your waveform window, and it'll keep track of how many matches that we have happening for that. So again, this is a form of functional coverage. It usually doesn't appear in your coverage report. It really depends on which tool you're using, which simulator. It'll often show up in your assertion report instead. Okay. Now for cover groups, this is very simple. We simply say cover group, in group, give it a name here, CG, give it a sampling event at pos edge clock. We can even gate our clock here. So we're saying if it's a decode. And then we can say, I want to cover all values of opcode with all values of mode. And so what's going to happen is the simulator is going to create little counters, keeping track of all possible values. We refer to these as bins. And you can see like the opcode has 3 bits, so 2 to the 3 is 8. So we're going to end up with 8 values here. And the mode is 2 bits, so we're going to end up with 4 bins for each of those values. And of course, when you look at this in a coverage report, you see this 0 here for the opcode 4. So that's a coverage hole. So it's very clear to see, hey, we need to go back, look at our stimulus, and figure out why we're not covering that. Now, in order to start collecting functional coverage, we have to instantiate this guy, right? So here we're going to say cover group name, which is CG, instance name CG underscore inst equals new. and now we start to get coverage. And where coverage is really useful is when we cross our coverage. So we say, I want to see all possible opcodes crossed with all possible modes. And now we can start to see certain patterns here. So over here on the right, you see this big pattern where for opcode 0 and 1 and across these modes, you know, if you saw that, that would clue you into something is not quite right. Either our stimulus isn't generating those cases. Maybe we have something in the RTL that's tied off because we've put it in a system and now we're not using part of the code or whatever. You have to go investigate that, right? This one here for opcode 3, well, that looks like we just didn't run enough stimulus. Probably just need to run a little bit more. And then you see this opcode 4. Notice it's not even occurring, is it? So that would clue us in to go back and look at our stimulus and see why. And in fact, for this example here, opcode 4 is an illegal instruction, which is why it's not happening. So why do we need hacks for SystemVerilog coverage? Don't we have everything we need? Well, the answer is no, there are limitations in SystemVerilog. So for example, you may have run into issues when you're trying to write a cover group and you want to grab a signal from one part of the test bench or design and another signal from another part. And it's not always so easy to grab these signals because when you define a cover point, it needs to be local. We're going to show you how to solve that one as well. Also, we have limited features. Well, have you ever written a cover group and you wanted to cross a cover point from another cover group with the cover point in your own cover group, right? So that you can't do that. So how do you solve that? We're going to talk about that as well. So example here is the cross coverage. Also, when you go when you look at your cross coverage, how do you filter out the things you don't want in there? It's not always intuitive what you end up getting, right? See a lot of head shaking. Yes, so you guys have been there. And then there are some keywords in SystemVerilog that don't behave like you think they do. And I'm going to talk about those last, some of the gotchas to watch out for. And another reason for this presentation is just because they have pretty much neglected coverage in the standard for what, almost 20 years now. However, this year there was a new version of the standard release, the 2023, and they actually made some enhancements to coverage. And I'm going to point out a few of those as we go through this. Okay. Yeah, it took 10 years. Yeah. Okay, so let's take a look at some of these hacks. The first thing I would encourage you to do is take advantage of your options in your cover groups. So built into every cover group are two implicit structures. One's referred to as option, as we show here, and one is referred to as type underscore option. These are referred to as your instance options here. So what we can do here in the top, you see it says per instance. So when you set this to something non-zero, now your simulator not only collects cumulative coverage, but also per instance coverage. So like if you want to see all the reads and writes across a certain interface, you can tell where everything's happening. When you set the per instance, then you can set some of these other things. We can set a weighting. We'll talk about that in a minute. At least says how many times we want to see something occur before we consider it covered. So I want to see 10 occurrences and then I consider it covered. You could set a goal here. We're setting our goal to 90%. Now, why you would set functional coverage to anything but 100%, I don't know, because if you wanted it, why'd you even include it, right? So I wouldn't use that one. But anyway, you can do it, and you can include a comment here, which would show up in your coverage report. So that's a good thing. And notice that you can set these options on per bin. So like, for example, here's an auto bin max. What auto bin max does is whenever you have a cover point and you don't specify the bins, your simulator automatically takes all the values and divides it up into a maximum number of bins. By default, that's 64. Here we're setting it to 128. Now you can set these options when you define your cover group, but you can also set these dynamically at runtime. If you have an instance of that cover group, you can just walk in using member notation here and set those values. Okay. Now, one thing you can do to make your cover groups more flexible and reusable is to add arguments to them. So when you do this, now we're passing in some of reference V, and we're passing in a string comment. So now notice we can use that V in our cover point. And so down here at the bottom where we're instantiating the cover point, we can pass in what signal we want it to cover. In this case, it'll cover A, the bottom one will cover B, and we can pass in a different string for that. Okay. One of the options, weight, you want to be a little careful with. So I actually recommend you use the weight because if someone goes off and writes a whole bunch of cover groups, and let's say you get 100% coverage on them right away, but that part of the design is just a little part of the design, it's going to make it look like you've done all this functional coverage when in fact it only matters a little bit, right? So I would recommend, look at your synthesis results if you can and kind of gauge what percentage of the design that block is, and then you could use that for your weighting. But where you need to be careful is the weight is not a percentage, it's a multiplier. What you're really saying here is, like, for example, in this coverage calculation at the bottom here, CG1 times 9, if module 1 is 9%, it's going to times that by 9 if we set the weight to be 9. Likewise here, we could set the second one to 5. If we fail to assign a weight here for the third one, it's going to default back to 1, which means we're actually going to get pessimistic coverage in that case because we didn't multiply it like we expected. Okay, so if you do use the weight option, use it everywhere. And if you don't use it, that's fine as well. But I think there's value in it so that you can get more of an accurate feel for how much you've covered. Okay. Now we also have another option that's available, and these are our type options. Type options apply to the whole cover group. We don't have as many options for type options, but there's a few of them in there. For example, you may not be aware, but we have like a dot strobe here, which says to do the sampling in the postpone region. In your simulator, the very last moment before it moves on to the next time step is called the postpone region. So if you want to grab the last known good value, no glitches, everything's been resolved, set the strobe here and you'll grab the last value. Okay. Now, since type options are per the cover group, it's kind of like a class-wide thing. And so we can do the same thing as with classes where we can use the scope resolution operator here and just say : type option and so on. So in other words, we don't need an instance of the cover group to actually set these things. Okay. If we have an instance, we can use it. Okay. Now, I mentioned that they've added some new features in the latest standard. And one of them is the ability to keep coverage on real numbers. See, you could only use integral values with cover points. And that's because an integral value is something you can slice and dice. You need to be able to slice it up into the different bin values. How do you slice up a real number? There's an infinite precision, right? So there's an infinite number of divisions you could do. So they added this new type option, real interval. So now we're saying 0.01 will be our smallest slice division. And so if you look at this first example here, B1, which is 0.75 to 0.85, that's going to create for us 10 bins, or this one here, 12 bins. Another thing they've added is a tolerance range. So here we can say in the bottom example, 0.753 plus or minus 0.01. And that's going to create for us these two bins down here. Okay. They've also added one other tolerance range, and that is plus % minus, which means plus or minus a percentage. So if you put 10 there, it'll take 10, multiply the thing, on the left here, and then use that as your plus or minus value. Okay. Now, I haven't found any simulator that implements this yet. So talk to your vendor. Maybe it's out there. I just haven't seen it yet. Okay. All right. So let's look at another hack. How do we handle when we have signals that aren't local to our cover group, and we want to include that in the cover group. Normally, we have the signals here in the local scope. We simply say cover point opcode, cover point mode. But what if it's in a whole nother class object or something like that, and we want to pull it in? Well, you might be tempted to use a hierarchical path name. The problem is the standard doesn't allow that. You must have a local signal. You can't use a reference there. So what's the workaround? Well, the workaround is to use those arguments again. Remember, we can pass by reference here. So here we're going to pass in an A and a B. And if you look at the bottom here we can put the hierarchical reference, right? Testbench.cov_unit A and so on. And now we can reach around our test bench, pull it into our cover group, okay? Here's another way that we can solve this problem, and that is by adding a sample method to our cover group. All you're doing is saying, when I sample, these are the arguments that I expect. And in fact, this example I'm showing you here is an example from a UVM environment with UVM RAL, because the RAL has hooks in there for calling the sample method. So here we're just saying we're going to pass in some object or structure called data, and we're going to pass in a direction, and then we'll use those for our cover points. Then when we call the sample method on our cover group, like we show here at the bottom, all we have to do is pass into it whatever values we want. Wherever they're coming from, it doesn't matter. Those are going to get passed in, and that way we can include those in our cover group. Okay. In this case here, this is a register model, but if this was a monitor or something, you might be grabbing stuff from an interface and throwing it over to some coverage collector and calling the sample method, passing those values back and forth. Okay. Now, in the latest standard, they've added a new feature called cover group inheritance. So remember I asked the question, what if I wanted to cross something from another cover group with something in this cover group? How do I do that? Well, the answer is there's no easy way to do that. But they have added this new feature which allows you to extend your cover groups. So now if I start with this cover group here, G1, and if I put it in a class, this doesn't work in a module, obviously, right? If I put it in a class, then I can extend G1, and I can either override what was in the original. Here I'm overriding color. Or down here in my cross, notice I'm using A, which is not defined in this class. It's inherited from up above. Plus I'm using D down here that I've added. So this is sort of kind of a partial step in that direction where you could at least extend and still get some reuse out of this. It's interesting they added this the way they did. I don't know about you, but this looks a little bit more like aspect-oriented programming than object-oriented programming, but that's what we have. And by the way, I don't think anyone's implemented this yet. But another thing to talk to your vendor about. Oh, and someone asked me this week, is this virtual? Like if you take a derived object and assign it into a base handle, is it virtual? And the answer is, we don't know, because they didn't define it in the standard. They define constraints to be virtual. There's an actual line in the standard that says it, but with this, they forgot to mention it. So we'll have to see how they implement it. I would assume it's virtual. I'm assuming that's how they'll implement, but we'll see. Okay, now let's look at another hack. This is something that you can take, utilize to kind of take advantage of this rich SVA syntax and combine these cover groups with your cover points. So for example, let's say we have our UVM environment here, and we have our interface where we're going to put these cover properties because we need someplace structural to do it. What we can do is we can have these cover properties monitor whatever behavior we want. And when they see the behavior, they can grab it, throw it on over to our UVM environment, and then we can collect our coverage. Okay, so here's an example. Let's say you can see in this example, we have a microprocessor here on the left. So we're going to create a sequence to look for some sort of jump instruction to come along. Up here on the top right with the diagram, you can see we have the fetch enable comes along and we fetch something on the data bus. Let's say this is a jump. So it's going to fetch an address to jump to, and then it's going to jump again, right? And that's why we have a fetch over here without any data, because it's making that jump. And so here in our sequence, if we just walk through this, you can see we have a fetch enable followed one cycle later where we grab, well, we check to see, did we get a jump? Did we get a jump 0 or a jump neg? And if we did, then we want to go ahead and grab whatever our value is on the data bus, put it into a local variable called opcode, grab the current address, my program count right here at the first fetch. Then I'm going to wait between 1 and $, so some indeterminate amount of time until I get another fetch. And then one cycle later, I'm going to unconditionally, that's why the 1 comma here is here. And then we're going to grab the address of wherever we jumped to. And now we're going to throw it all into a function. So we've got some cover jump function somewhere that will pass in the opcode, the starting address, and the target address. And then to kick the whole thing off, we need to put it in a cover property, and that'll spawn the thread of execution. Okay, now where is the cover jump defined? Well, it's in our interface. Here it's just a function where we're going to pass in the opcode and the start and target address. We're going to package that up into jump data. Let's say this is a structure. And then we're using this variable here called jump trigger. Now, you guys may be familiar with Verilog events. You ever seen that where you just say event? It's called a named event, and then you use the trigger syntax. But in Verilog, whenever you modify a signal, you generate an event. So that's what we're doing here, is we're generating an event by simply using the tilde and toggling the signal, okay? And then in our monitor, we have some process that's waiting for the event to happen, the jump trigger. And when it does, then we reach into the interface, we grab out the jump data, we package it up into our transaction, and we write it to our coverage collector using our analysis port. And of course, analysis ports need a write method. So we're going to have to implement the write method in the coverage collector over here. And so inside the write method here, we set everything up in our cover points, and then we call sample on our cover group, and then it all gets put in the cover group. So instead of having to write some big state machine to grab the scenario, we've taken advantage of the SVA syntax, and we've linked it into our cover group so that now we can do cross coverage, right? And maybe check to see if other scenarios were happening, right? So, okay, so again, we get the best of both worlds. We get that rich temporal syntax with the cover property, and we get the cross coverage with cover group. Okay, now here's another hack that I shared this with someone this week, and they found this very interesting, is you can use coverage to direct your stimulus. If you want a really quick way to fill your coverage holes, this is the trick right here, okay? But I'm not sure I really want you to know this because I'm not sure it's the right thing to do, but I'll talk about that in a minute. All right, so built into every cover group, cover point, and cross is a method called get coverage. And this method returns back a real value of what percentage are we covered. So for example, in the top here, we're going to do this loop 100 times. We're calling sample, and we say, give me the coverage. Here, if coverage is greater than 90, then I can say stop collecting coverage. So this could be one way to turn coverage off. Why would you turn it off if it's 90? I would wait till you get to 100 to turn it off, but you might want to turn it off once you've gotten everything filled, maybe for performance reasons or whatever. Okay. Well, we can also use get coverage to bias our stimulus. So in this bottom example here, we're using a RAN case. And remember that RAN case, you specify basically weights to say which percentage, what probability are we going to select that case. So here what we're doing is we're reaching into our cover group. Let's take the first one here for cover group A. We're saying, give me the coverage of A. Let's say A has been hit 90%. So that would return back 90, and we're calling $RTOI, which is real to integer. So we're converting it to an integer. So 100 minus 90 would be 10. So basically this first line would be only a weight of 10, whereas if these guys had never been hit, it'd be a weight of 100, right? In other words, we're biasing which direction we're going to go. Okay. Now that works well in this case here with just the A and B, but what happens when you start to add bins? So normally we don't usually just do a cover point on all possible values. We go in and we filter it down. We make ranges like we have right here. Here we've created, 3 bins of the hundreds or whatever is interesting. That's the things we want. The problem is if we call get coverage on it, it doesn't work because get coverage is not defined to work on bins. It's defined to work on cover points. So then how do I use this trick? Well, the workaround is to duplicate your cover points. In other words, notice we're using the same instruction word in all these cover points, but we're specifying only one bin in there, the thing that we're looking for. Now I can, down here at the bottom, I can say, give me the coverage on my no ops because I've defined the no ops. So it's a little bit syntax intensive. You have to kind of do a bit of typing here, but it works. Okay. Okay, now how could I use this like in a UVM environment? Well, I could create a bunch of variables, some weights, and then I could even use this in a random constraint. So remember the disk constraint, you're specifying your different probability weighting here. So I'll set everything to 1 to start out with, so we have an equal probability. But before we do the randomization, we want to update the constraints. So here we've created this function on the top called calcweight, and notice we're doing the same thing. We're going to grab the coverage, and then we're going to subtract it from 100, and we're going to add 1 just to make sure it's not 0, because that would just turn it off, right? And then down here in our pre-randomize, before we actually do the randomization, we'll come in and we'll update all of our weights. Then the randomize takes place with those updating, and this will bias our stimulus, okay? If you want a really quick way to fill your coverage, this will do it. However, is it random? I don't think it is, because you just inserted intelligence into this, didn't you? So the question is, should you do this or not? Well, I'm going to let you decide. The whole reason why we do random testing is to test the things you didn't think about. And once you start coming in, well, we had a talk earlier about using AI to avoid duplicating things. Well, the same argument applies there too. Should we be not duplicating because maybe there's a scenario we hadn't thought about? I don't know. I'm going to leave that up to you to decide. So use this with caution, but this does work, and it actually works pretty quick at filling those coverage goals. Okay, well, another thing you might want to do is if you're going to use cover properties, how do we get them into our regular coverage report, especially if your tool doesn't normally do that? How can we get them as part of our cover groups coverage? Well, one thing we could do is we could create some sort of variable. I'm going to use a hash table or associative array here, right? And so here, when we get a match on C1, so A implies B, we'll go ahead and set a 1 saying we got a match. Likewise on cover group 2. Then all we have to do is create a cover point for that particular hash entry. And in fact, we could reduce this down to just, I want to see if I got a match. If you do it this way, it's kind of like you're either on or off. And so we'll be clearing our coverage array anytime we're, on the neg edge here. You may want this to actually be just like a plus plus, so it just keeps track of how many values. You might want to do it that way, but it's up to you. But if we do this, then this gets included as part of our cover group coverage, okay? And the advantage of this is now I can cross what just happened. Back here, I'm only looking at whether A implied B and C implied D, but now I can cross this and see, did I see both of these happening at the same time, or whatever functional scenario you want to do. Okay. Okay, so I saw a lot of people agreeing with me that it's difficult, or at least non-intuitive, as to how to filter your cross coverage. So let's take a look at this. So if we go back to that first example where we have opcode crossed with mode, we saw that we had some pretty blatant holes in here, and we're going to want to filter those things out. So if we ran this through our simulator and did a report, you would see right away that we've got some holes here, these element holes, and we have some uncovered bins showing up. Well, there are two ways to filter out coverage. Either we ignore bins, and with ignore bins, what it does is it takes whatever you tell it to ignore and it just pulls it out of the coverage calculation. Since we've removed this opcode 4 over here out of the the cover point, it'll no longer show up in our cross. But there's another way that you can remove coverage, and that is to actually define the coverage you want to see. So for example, I could come down here in my cross and I can say I want to see all bins with no holes. So I want to see all bins of opcode and mode with opcode greater than 1, which gives me everything to the right of this big hole here, right, on the left here, and or mode 0, which means it gives me this bottom line here. That would filter out all these holes from my cross. So if we ran this through simulation, here's what we get. Unfortunately, it didn't actually work. And the reason is, by default, your simulator automatically creates bins for you for all those values you didn't specify. And so even though we know that we have 100% coverage, notice what percentage we end up with here, just 14%, because it added in all these other values that we weren't even interested in. So what's the solution? Well, one solution is to use a new feature that's been added into the standard, and that is called cross-retain auto bins. So you could turn this off, and in theory, that would remove all those auto bins, and you'd only get the thing that you specified. Unfortunately, I can't show you an example because it hasn't been implemented yet, but it will be. So what is the right solution? Well, we need to probably use ignore bins, but the easy way to do it is specify what you want, like we show here, and then just take the same expression and invert it, like we have inverse it here, where we're just saying we're putting the not symbol in front of our condition here and say ignore that. And now that does work. Okay. I don't know do I have an example? No, I don't. But yeah, just add this inversion here and that works. Now there's one other way to filter cross coverage, and this is a surefire way. It gives you ultimate control. And that is you can create coverage tuples. In other words, you can say exactly which row and column you want. So here in this example, we've written a function, and this function will return back a Q. Okay, and you can see this function is going through every opcode. So the first for loop is opcode 0 through 7, and then each mode 0 through 3. And then we're saying if the opcode is 4, that one column we want to take out, or the opcode is less than 2 and mode greater than 0, then we're going to add them to this set. And really what we're saying here is this opcode is your column, the mode is your row. So column and row, and then you pass that back to your ignore bins here, and that will actually pull out all those things from your coverage. Now, in this case, we used a function to do this. you don't need to use a function. You could actually come in here using set notation. You could just manually write it out. I want to see 0, 1 and 0, 2 and blah, blah. You can write all that out by hand if you want, but using a function is kind of, quicker in my opinion, but not as maybe as intuitive. But this gives you full control. And that's certainly something to consider if you're struggling with your intersects and different things, trying to pull out that one value that's just like an oddball thing, trying to get it out there. Okay. All right. Last but not least, what are some things to avoid? Well, the first thing I want to talk about is illegal bins. Now, a lot of people like illegal bins. Illegal bins does the same thing as ignore bins. It removes that value from the coverage calculation. So here, in this case, we're just ignoring value 4 because we know it's illegal. But what illegal bins does also is it adds a check. So if it ever sees this value occur, it throws an error. In fact, do I have an example here? Yeah, right here's an example. You can see it said error, illegal range bin, value, whatever got covered. So it actively throws this error. The question I have for you, though, is should a passive component like a cover group be actively throwing errors? Yeah, I don't think so either. We had no, as someone said no. Yes. I philosophically think this is wrong because let's face it, it's like my calculus professor used to say, what's our main motivation in life? Laziness. We want to find the quickest solution to the problem, right? And that's what we do is we throw it in there and say, oh, it's going to be checked. But do you always run with coverage on? No, because it takes up a lot of cycles. So why would you want to rely on something that's not always going to be turned on to do your checking when you're going to do most of your stimulus without your coverage? I think philosophically this is wrong. You should write an assertion, write your check, and then use ignore bins for your coverage. Okay. Now, another thing that you may be tempted to use is the default keyword. Default, what it does is it's kind of like a catch-all. So here we've defined a bunch of values, a bunch of bins, but you can see we haven't defined everything. This tiny bin only goes to 100. This huge bin goes from 1,000 to $1. Now, $1 here in this context means the maximum range for this variable, which is 2 to the 16, so about 65K. But we still haven't gotten everything because we haven't defined, 101 to 200 and 201, blah, 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 right? So default comes along and just mops up everything that you didn't include. And that's a good thing. Sometimes we just want to mop things up. But there's two problems in this example. First of all, notice that we're using an open range here. What that means is auto bin max doesn't apply. Means if you have 1,000 values over here, it's going to create 1,000 bins. That's probably not what you wanted. In fact, if we look at an example here, what if we do this with int a? How many values are there? 4 billion values, right? And in fact, here's an example from a simulator. After about 2 billion values, it gave up, right? So that's a bad thing. I would always recommend don't use an open range here when you're doing this. But the other problem is that the default keyword pulls those values out of the coverage calculation. What if you just wanted a catch-all that included it all in there? So for example, over here, look what happens. When so here I'm taking all possible values, binning them into 4 bins, but because it pulls it out of the coverage calculation, now I've got 0 coverage for cover point A. So when I cross it, guess what I get? 0 coverage for my cross. It's not what I expected, right? I wanted something that could just kind of mop it all up and kind of show me that I had some other values, maybe a range of values. Doesn't work. So what do you do in that case? Well, if you really want to use the default keyword, that's fine. You can put it with the other, but don't use the open range. Again, that's not going to be included in your coverage. The better solution is probably to use your dollar sign, because dollar sign on the left-hand side of the range means minimum value, right hand means maximum value, and then maybe just use a wildcard bin here and grab any values. And that way you know exactly what's being mopped up, you know. Okay. All right, guys. So hopefully you found those hacks helpful. I'm sure there's other hacks even you could share, because there are limitations with this stuff. I mean, it works pretty good. We've been using it for a number of years. Hopefully they'll continue to making more improvements. But I know, having talked to one of the guys on the committee, he admitted that it's been neglected for many years. And so I guess they're finally just now starting to get around to it. So uh, probably worth, if you guys have suggestions, letting them know that as well. But by the way, of course, you guys know Doulos is a training company. If you are interested in any of our training classes, just throwing this up there, let us know if we can help you with SystemVerilog or anything. And if you're interested in some more tips and tricks, you can go to DVCon's website, type in 2011 US here, and look for this paper here, which a lot of the content came from, but I added some new stuff. And I also have some things in this paper. Maybe you're interested in using the DPI or VPI to access some of the different things. I have some examples in there. So go check that out and you can get some more tips and tricks. Okay. All right, guys. Are there any questions? Any questions online? Not so far. Okay. Yeah, question. Uh, I think that you would use your per instance only if you really needed per instance, right? Like if you really needed to see all the reads and writes across an interface, I mean, you can't get away from it. If you need the coverage, you need the coverage. You know what I'm saying? But yeah, if you don't need, if you can just live with cumulative, I wouldn't turn it on. That would be my solution. As far as the weighting goes, that's really just a calculation. It's not like it's adding more memory or anything. It's just part of the calculation. Yeah. Okay. Any other questions? Yeah. Okay. Yes. Yeah. Yeah. Let's see if we can find it here real quick. This one right here. Oh, were you talking about on the filtering, the cross coverage? No, it was this one right. Sorry. This one right here. Yeah, so you can see that the filter function's being called here with the ignore band. There it is. Okay. Any other questions or comments? Anybody here ever struggle with coverage, filtering coverage? Somebody? Never. Every project. No, it's supported. I mean, honestly, I sometimes find, well, I find that the intersect is non-intuitive for many people, at least like in assertions, intersect is not necessarily. I mean, it's sort of intuitive here, but yeah, if you use with, you can kind of just say exactly what you want it to do. But yeah, no, I guess it's a preference, personal preference thing. So yeah. Well, you can create an exclusion list right here by just using set notation like you would with an associative array. So it would be, you'd create little sets of column, row, column, row, column, row, and this would say which ones you want to exclude. that make sense? Oh, that type of exclusion, that's a tool specific thing, and that's more of a tickle. That's tickle. So, no, that's a different subject because this is built. This is the language. Yeah, yeah. But was there something specific you wanted me to talk about, or? Oh, right. Yes, you can always kind of override things with tool options. Yeah, yeah. So, any other questions or comments? Anything online? No. All right, guys. If not, I appreciate you sticking around to the end of the day and sticking around with me. So if you have any questions, comments, please feel free to give me a shout or talk to me afterwards. Be love to have a chat with you. Okay. Thanks, guys.